In the unforgiving world of military aviation, there are few environments more hostile to man and machine than the deck of an aircraft carrier. It is a 4-acre patch of sovereign steel adrift on a hostile ocean, a place where the laws of physics are not merely respected, but wielded with controlled, explosive violence. Here, every bolt, every hydraulic line, and every composite panel is an argument against entropy, a testament to engineering pushed to its absolute limit. The outcome of a future naval battle could well be decided by the molecular integrity of a landing gear strut or the microsecond response of a flight control computer. It is into this crucible that the People's Republic of China has thrust its most ambitious naval aviation project, the Shenyang J-35. This aircraft is far more than a new fighter. It is the capstone of a generational ambition, the sharp, stealthy tip of a spear that includes the Type 003 Fujian supercarrier and its revolutionary electromagnetic catapults. The successful integration of the J-35 is not merely a test of an airframe, but the validation of an entire national strategy to project power across the blue waters of the Indo-Pacific, rewriting a strategic calculus that has stood for 3/4 of a century. The roar of its engines and the silent, powerful fling of the electromagnetic launch system, EMALS, are the sounds of a new chapter in naval history being written. To understand the machine built to tame this environment, one must look not to the sea, but to a corporate rivalry on land that gave birth to a fighter in search of a mission. The J-35's lineage is unorthodox, a story of corporate ambition, state rejection, and eventual strategic redemption. It began life as the FC-31 Gyrfalcon, a private venture by the Shenyang Aircraft Corporation, SAC, born from the ashes of defeat. SAC had lost the prestigious JXX fifth-generation fighter competition to the rival Chengdu Aircraft Industry Group and its formidable J-20 Mighty Dragon. While Chengdu received the full backing of the People's Liberation Army Air Force, PLA-AAF, SAC pressed on, developing the FC-31 as a corporate-funded hedge, a technological demonstrator aimed squarely at the export market. For years, the project languished in a state of semi-secrecy, a technological orphan without a clear domestic role. Its public debut was less a grand unveiling and more a series of cryptic appearances. In June 2012, a partially assembled airframe was photographed on a police-escorted flatbed truck, heavily wrapped in camouflage, sparking fevered speculation that it was everything from a new Hongdu JL-10 trainer to an elaborate piece of agricultural machinery. When a fully assembled prototype bearing the registration 3101 finally emerged, the military observation community, never short on imagination, bestowed upon it a flurry of unofficial names: J-21, J-31, F-60, Snowy Owl. This period in the wilderness, stretching for nearly a decade, was defined by iterative, under-the-radar development. The FC-31 was a fighter without a state requirement, its evolution driven by corporate funds and the hope of attracting a foreign buyer who couldn't get their hands on an American F-35. This process, however, inadvertently fostered a unique dynamic within China's defense industrial base. It created a dual-track, competitive model, preventing the technological monoculture that can arise from single, state-sponsored programs. The result was two distinct fifth-generation airframes: the large Canard Delta J-20, optimized as a heavy land-based air superiority interceptor, and the medium-weight, more conventional FC-31. In a twist of industrial irony, the very characteristics that made the FC-31 a less compelling choice for the PLAF, its smaller size and its twin-engine configuration, made it the ideal candidate when the People's Liberation Army Navy, PLAN, finally crystallized its requirement for a carrier-based stealth fighter. The twin engines offered the overwater redundancy and safety margin prized by naval aviators, while its more compact footprint was inherently better suited to the crowded, high-tempo environment of a carrier deck. The corporate failure had, through serendipity and persistence, become a vital national strategic asset. The physical architecture of the J-35 is a masterclass in modern, low-observable design principles, a metallic ghost shaped by the competing demands of aerodynamics and radar invisibility. The airframe, stretching 17.3 meters from nose to tail, employs a blended wing-body configuration that smoothly merges surfaces to eliminate hard, radar-reflective angles. Its most prominent features are the forward-swept diverterless supersonic inlets, DSI, distinctive bumps ahead of the engine intakes that manage airflow at supersonic speeds without the complex, heavy, and radar cross-section increasing mechanical ramps of older fighters. These inlets feed air into serpentine S-ducts, curved tunnels designed to mask the highly reflective turbine fan blades from frontal radar interrogation, a critical feature for any credible stealth aircraft. The entire geometry is a study in edge alignment, where the angles of the trapezoidal wings, canted twin vertical stabilizers, and panel edges are carefully controlled to deflect radar energy away from the emitter. The extensive use of sawtooth patterns on landing gear doors and internal weapons bay edges further scatters incident radar waves. This meticulously shaped exterior is constructed from a high percentage of lightweight composite materials and coated with layers of radar-absorbent materials, RAM, designed to absorb electromagnetic energy rather than reflect it. The manufacturing process itself reflects a generational leap, with reports from inside SAC's production facilities describing a modular digital workflow with robotic riveting systems and the use of digital twin technology for modeling aerodynamic stress, mirroring the advanced Industry 4.0 processes used by Western manufacturers. Yet, for all its aerodynamic and material sophistication, the heart of the J-35 and the pacing item for its entire development has been its propulsion system. The program's evolution is a story of China's long and arduous quest to break its dependency on foreign engine technology. The original FC-31 prototype flew with Russian-made Klimov RD-93 engines, a reliable but dated power plant that represented a significant strategic vulnerability. Subsequent iterations saw the integration of interim Chinese engines like the WS-13E, an upgraded derivative of the RD-93. The definitive power plant, however, is the indigenously developed WS-19 Huangshan, a medium-thrust afterburning turbofan reportedly generating around 13,000 kgf of thrust per engine. Achieving this milestone has been the program's central struggle, plagued by persistent challenges in material science, metallurgy, and manufacturing consistency that have historically held back China's entire aerospace sector. Even with the WS-19 design reportedly complete, mass production has been hampered by supply chain bottlenecks for the advanced single-crystal alloys required for high-pressure turbine blades. In a display of pragmatic risk management, there are indications that initial production batches may feature a two-engine strategy. The naval J-35 could be equipped with the more mature WS-21, a heavily improved WS-13 derivative, providing a reliable, well-understood engine for the punishing carrier environment, while the land-based J-35A assumes the integration risk of the newer, higher-performance WS-19. This phased approach aims to get a credible capability to the fleet as quickly and safely as possible, acknowledging that in the world of jet engines, the leap from a working prototype to a reliable, mass-produced power plant is a chasm that has consumed decades of effort. Transforming the land-based FC-31 airframe into the sea-going J-35 required a profound re-engineering effort, adapting it to withstand the unique and brutal physics of carrier operations. This was not a matter of minor tweaks, but a fundamental redesign of the aircraft's entire lower structure. The landing gear in particular was beefed up to a degree almost unrecognizable from its terrestrial progenitor, engineered to absorb the immense forces of a controlled crash onto a pitching, rolling deck at sink rates that would shatter a conventional undercarriage. The naval variant features a robust twin-wheel nose gear, a hallmark of carrier aircraft that provides greater stability and durability during high-stress launches and recoveries, replacing the single-wheel arrangement of the land-based version. Integrated into this strengthened nose gear is a catapult launch bar, the critical mechanical link that engages with the shuttle of the Fujian's electromagnetic catapult system, allowing the aircraft to be accelerated from 0 to takeoff speed in under 3 seconds. At the rear of the aircraft, a heavy-duty arrestor hook was added, designed to snag one of 4 arresting wires stretched across the carrier's landing area to bring the 28,000-kilo machine to a violent halt. To manage the finite and precious real estate of a carrier's flight deck and hangar bay, the J-35 incorporates a complex wing-fold mechanism, allowing its 11.5-meter wingspan to be reduced for compact storage. The sum of these modifications, strengthened airframe, navalized gear, launch bar, arrestor hook, and folding wings, represents an engineering feat that has historically been the preserve of a very small club of nations. The ultimate validation of this effort came during the Fujian's sea trials in 2025, when a J-35 successfully performed a catapult launch, a landmark event that made China only the second nation to electromagnetically launch a stealth fighter from a carrier. This achievement is less about the aircraft in isolation and more about the successful integration of 2 colossally complex systems, proving the viability of China's entire next-generation carrier strike group concept in a single, powerful stroke. Intriguingly, the plan's doctrine appears to embrace a degree of cross-deck flexibility. The appearance of a full-scale J-35 mock-up on the deck of the older, ski-jump-equipped carrier Lineage suggests a deliberate strategy to make the fighter compatible with the entire fleet, not just the new catabar-equipped vessels. A ski-jump launch, STOBAR, would impose significant penalties on the J-35's maximum takeoff weight, restricting its fuel and weapons load. However, even in this constrained capacity, it would provide the older carriers with a 5th-generation stealth capability they desperately lack with their current complement of non-stealthy J-15s, dramatically enhancing their survivability and situational awareness. This points to a 2-tiered deployment strategy. J-35s operating at their full potential from the Type 003 and future carriers, while also serving as a critical, if compromised, upgrade for the rest of the fleet, accelerating the modernization of China's entire carrier force. Beyond the sculpted composites and powerful engines lies the J-35's true essence as a 5th-generation combatant, its digital nervous system. This invisible architecture of sensors, processors, and data links is what elevates the aircraft from a mere flying machine to a node in a vast networked battle space. The primary sensor is a large, active electronically scanned array, AESA radar, housed in the nose, reportedly based on advanced gallium nitride, GaN modules, which allows for the simultaneous tracking of multiple targets at ranges exceeding 200 kilometers, all while possessing a low probability of intercept. Complementing this active sensor is a suite of passive systems designed for stealthy observation. A chin-mounted electro-optical targeting system, EOTS, broadly analogous to that on the F-35, provides long-range detection and precision targeting of air and ground threats using infrared imaging, allowing the J-35 to identify and engage targets without emitting a single radar wave. This is augmented by a distributed aperture system, DAS, a network of 6 infrared cameras embedded around the airframe that provides the pilot with a seamless 360-degree spherical view of the surrounding environment, offering unprecedented situational awareness and missile warning capabilities. However, the hardware is only half the story. Chinese sources frame the J-35 not as a lone wolf, but as a software-defined sensor node and a kill chain quarterback. The core ambition is for the aircraft's central computer to perform true sensor fusion, algorithmically integrating data from its own radar, EOTS, and DLS with off-board information streamed via secure data links from other assets, like the KJ-600 Airborne Early Warning and Control AEW&C aircraft, Type 0555 destroyers, and other J-35s. This creates a single, unified tactical picture that is far greater than the sum of its parts, allowing a flight of J-35s to operate as a cohesive data-sharing team, with some acting as passive sensors, while others engage targets cued by the network. This networked capability is critically dependent on the simultaneous development of the carrier-borne KJ-600, which acts as the high-altitude eyes of the fleet, detecting threats at extreme range and allowing the J-35s to remain electronically silent for as long as possible. To prosecute these threats, the J-35 features a large internal weapons bay capable of carrying a formidable payload while maintaining its stealth profile. Its primary air-to-air armament includes the PL-15, a very long-range missile, and potentially the even more advanced PL-21, supplemented by the PL-10 high-off-boresight missile for close-in engagements. For strike missions, it can carry a variety of precision-guided munitions and anti-ship missiles, with a total payload capacity of up to 8,000 kg when utilizing its 6 external hardpoints for non-stealthy missions. Yet, for all this advanced hardware, the most significant challenge for China lies in the code. Sensor fusion is a domain where a single misplaced semicolon can ground a billion-dollar fleet. It is not merely about displaying data streams on a screen, it is about creating a stable, trustworthy, and intuitive picture from disparate, noisy, and sometimes conflicting inputs. This capability is the product of millions of flight hours, a colossal simulation and testing infrastructure, and decades of institutional learning, an informatic gap that represents the true battlefield in the contest between the J-35 and its Western counterparts. Any discussion of the Shenyang J-35 inevitably leads to a comparison with its American analog, the Lockheed Martin F-35 Lightning II. The visual resemblance is undeniable, leading to frequent and not entirely unfounded accusations of design theft and cyber espionage. However, to dismiss the J-35 as a mere clone is to overlook the deep-seated divergences in design philosophy, driven by different national constraints and operational priorities. The most fundamental difference is the J-35's twin-engine configuration versus the F-35's single, immensely powerful Pratt & Whitney F-135 engine. This was not an arbitrary choice. The F-35's entire design was famously compromised by the tri-service requirement to produce a short takeoff and vertical landing, pseudo-VL variant for the U.S. Marine Corps, the F-35B. This necessitated a single, massive engine with a complex lift fan system, a constraint that shaped the aircraft's entire airframe. Freed from this STOVL requirement, Shenyang's engineers opted for a twin-engine layout, a more conventional and arguably more logical choice for a carrier fighter, prioritizing the over-water redundancy and safety that two engines provide. This also reflects the reality of China's domestic engine industry, which has yet to produce a single engine with the thrust and reliability of the F-135. In terms of raw performance, the two aircraft present a mixed picture. The J-35, with its twin WS-19s producing a combined thrust of around 46,000 pounds, boasts a higher top speed, estimated at Mach 1.8, or even as high as Mach 2.2 compared to the F-35's Mach 1.6. The J-35 is also credited with a slightly longer combat radius, estimated at 1,200 to 1,350 kilometers, versus the F-35C's 1,240 kilometers. However, the F-35 holds a decisive advantage in what is arguably the most critical metric for a fifth-generation fighter: stealth. The F-35's all-aspect radar cross-section, RCS, is estimated to be as low as 0.0015 square meters, the size of a metal golf ball. The J-35's frontal RCS is estimated to be around 0.01 square meters, still highly stealthy, but an order of magnitude larger. Furthermore, the F-35's unmatched sensor fusion, the product of a multinational program with over 1 million flight hours, remains its trump card. The J-35's effectiveness will ultimately be determined not by its ability to match the F-35's kinematic performance, but by its ability to close this vast gap in software maturity, global sustainment logistics, and the operational doctrine built upon them. The J-35 does not need to be superior to the F-35 in every respect to be strategically transformative. Its primary role may be to act as a good enough peer adversary that shatters the West's monopoly on carrier-based stealth. By simply existing in operationally significant numbers, it fundamentally alters the combat calculus for U.S. naval forces, eroding the technological overmatch they have long enjoyed, and forcing a drastic change in tactics, risk assessment, and resource allocation. It is an instrument of asymmetric competition, designed not necessarily to win a one-on-one dogfight, but to raise the cost of intervention to a prohibitive level. The operational deployment of the Shenyang J-35 aboard the Type 003 Fujian marks the beginning of a new era, not just for the plan, but for the entire strategic landscape of the Indo-Pacific. The aircraft is the critical enabler for the plan's transformation from a coastal defense force into a true blue-water navy, capable of projecting sustained, credible air power far from China's shores. A carrier strike group equipped with a survivable fifth-generation air wing is no longer a limited regional asset, but a mobile bastion of sovereign power, capable of influencing events thousands of kilometers from the mainland. The J-35 is the linchpin for the extension of China's anti-access area denial, A2AD strategy. Carrier groups centered on the Fujian can now push this defensive bubble deep into the Pacific, potentially holding at risk assets and bases along the second island chain, and directly challenging the U.S. Navy's freedom of action in the Western Pacific. The future prospects for the J-35 platform involve continuous modernization, likely including the integration of artificial intelligence for decision support, advanced electronic warfare suites, and the command and control of unmanned loyal wingman drones. However, perhaps its most significant future impact lies in the revival of its original mission: export. The potential sale of the J-35 to nations like Pakistan represents a second front in its competition with the F-35, moving from the military-technical domain to the geopolitical one. Such a sale would provide Islamabad with a fifth-generation capability that its regional rival India currently lacks, threatening to ignite a new and technologically advanced arms race in South Asia. More broadly, it would establish China as a premier global supplier of high-end military hardware, breaking the West's long-held monopoly and creating an alternative for nations not aligned with the United States. The J-35 is therefore more than a machine of war. It is a potent instrument of national will, a symbol of technological achievement, and a new center of gravity in the shifting global balance of power.